the ability to adhere to nearly any surface, from metal and plastic to glass, adhesive tape has replaced millions of welds and rivets in modern manufacturing. It's become the go-to solution for fast, lightweight, and durable bonding across industries worldwide. From molten polypropylene pellets, humans stretch the material into thin films, treat it with high-voltage electricity, coat it with acrylic adhesive, and slice it into billions of small rolls, all to create a sticky layer thinner than a strand of hair, yet strong enough to hold together the world of goods. Join us as we explore how humans transform streams of hot plastic into rolls of tape, the silent material that keeps the machinery of modern production running every single day. To create what may look like a simple roll of tape, the process begins with a material known for its remarkable mechanical properties: polypropylene, a lightweight, flexible plastic that can withstand tension several times higher than ordinary polyethylene. Tons of resin pellets are delivered to the factory in sealed containers to prevent moisture contamination, since even the slightest trace of water can reduce the film's clarity and structural integrity. Before melting, each batch is dried at about 230 degrees Fahrenheit, completely eliminating moisture and stabilizing the polymer's characteristics. Then, a precise blend of additives is introduced: thermal stabilizers to resist production temperatures reaching 500 degrees Fahrenheit, anti-static agents to prevent dust accumulation, and adhesion enhancers that help the glue bond firmly to the film surface. The blending takes place inside a closed high-speed mixing system where every parameter, from duration to internal pressure, is constantly monitored by sensors. The result is a pure, uniform polymer mixture, ready for the next step, forming the transparent base film, the backbone of every roll of adhesive tape. From the molten polymer mixture, the hot resin is pushed into the circular die head of the film blowing machine under extremely high pressure. Inside, the material is evenly distributed around the die opening through a spiral flow divider that stabilizes the flow and prevents thickness deviations. As it exits the die, compressed air inflates the molten tube from within, forming a thin, transparent cylinder known as the film bubble. The size of this bubble is precisely controlled by air pressure and airflow volume to maintain uniform thickness across the entire surface. During inflation, the polymer chains are stretched simultaneously in two directions, longitudinal and transverse, giving the film remarkable tensile strength, excellent impact resistance, and minimal deformation during use. Once the bubble is formed, a cooling ring surrounding the die blows cold air evenly from every direction, rapidly reducing the temperature from over 450 degrees Fahrenheit to safe levels within just a few seconds. When the bubble reaches a stable size and tension, it moves toward the flattening zone, where a series of precision-aligned steel rollers guide it with accuracy down to fractions of an inch. Two opposing rollers gently press together, collapsing the bubble into two flat, parallel layers of film. This roller system not only winds the film, but also stabilizes the surface and evenly distributes stress across the full width of the material. Each roller is locally heated or cooled to maintain consistent temperature, preventing shrinkage, adhesion, or surface wrinkling. A temperature difference of just a few degrees Fahrenheit can cause deformation or reduce clarity. By the time it passes through the final rollers, the twin layers remain lightly fused, forming a smooth, flat, and crystal clear sheet of film, the completed base material for the next stage of production. In addition to the film blowing process, some factories use cast film technology to produce the plastic base layer for adhesive tape. In this method, the molten polymer is not inflated, but is instead pressed directly through a flat die with a narrow slit only a few thousandths of an inch wide. The continuous flow of liquid resin spreads evenly onto the surface of a high-speed rotating chill roll, forming a thin film with perfectly uniform thickness. This technology allows for more precise control of film thickness and flatness, thanks to the immediate cooling that occurs as the polymer comes into contact with a metal roll cooled by circulating water at around 60 to 70 degrees Fahrenheit. Rapid cooling freezes the polymer's crystalline structure, creating a surface that is smoother, glossier, and optically clearer than blown film. Compared to the blown film method, cast film has less deformation, making it ideal for adhesive tapes that require absolute flatness for coating or logo printing. Some factories also integrate multiple material layers within the same process, such as anti-static coatings, tear-resistant reinforcements, or adhesion boosters. By combining several extruders operating simultaneously to create a multi-layer film only a few mils thick. Thanks to its stability and high uniformity, the cast film process has become the preferred choice for premium adhesive tapes, where every inch of material must maintain identical tension, thickness, and adhesive response with pinpoint accuracy. Once the film has been formed, the material moves to the coating section, the stage that gives adhesive tape its signature sticking power. The film roll passes through a precision-controlled coating system where an ultra-thin adhesive layer only a few microns thick is evenly spread across the entire surface. Depending on the type of tape, the adhesive may be water-based acrylic, known for its durability, heat resistance, and aging stability, or synthetic rubber, which provides instant tack and greater flexibility across various materials. The adhesive is continuously stirred inside a sealed mixing tank to maintain consistent viscosity before passing through the coating rollers and a fine steel blade that regulates layer thickness with micrometer precision. After coating, the film travels through a heated drying chamber maintained between 180 and 220 degrees Fahrenheit, where solvents or moisture are evaporated, leaving behind a clear, uniform, and firmly bonded adhesive layer. Some premium tapes are coated twice, a base layer that strengthens adhesion to the film, and an outer layer optimized for performance during application. As the coated film exits the drying chamber, it is cooled and rewound into large, flat, glossy rolls, smooth, dry, and ready for the final finishing stages. While the adhesive film is being coated, another production line in the factory is dedicated to preparing the paper cores, the cylindrical frames that support each roll of tape. Though they may seem secondary, these cores play a critical role in maintaining stability, tension, and flatness during high-speed winding. To produce them, specialized suppliers use long fiber craft paper, valued for its compression strength, moisture resistance, and dimensional stability. The paper is first wound into large jumbo rolls, then passed through a coating unit where PVA, or starch-based adhesive, is evenly applied by a low-speed rubber roller, forming a thin, consistent layer that ensures tight bonding between paper sheets. Next, the core winding machine feeds the coated strips onto a steel mandrel set at an angle between 30 and 45 degrees. As the layers spiral, pressure rollers apply roughly 150 psi, compressing each layer uniformly to create a dense, gap-free structure. A servo sensor synchronizes mandrel rotation and paper feed speed, ensuring the helical pattern remains perfectly aligned. When the desired thickness is reached, carbide alloy blades are activated to automatically cut the tube into pre-programmed lengths. Along the cutting assembly, multiple thin blades are arranged in parallel, each spinning thousands of times per minute and producing a faint, sharp hiss as they slice through the craft paper. Laser sensors continuously track both position and speed, ensuring every cut achieves an accuracy of 5/1000ths of an inch, so that each core maintains exactly the same width. The finished cores then roll smoothly along stainless steel conveyor rollers, where optical sensors count them one by one and automatically stop the line once the preset quantity is reached. From there, the cores slide gently into rubber-lined collection bins, preventing impact damage to the freshly cut edges. At this stage, workers perform random inspections to verify roundness and concentricity before sending the entire batch to the film winding section, where these cores become the very centers of every completed roll of adhesive tape. Once the paper cores have been completed and inspected, they are transferred to the tape winding line, where the adhesive-coated film is precisely wound around each core. Each core is mounted either manually or by robotic arms onto the main spindle. Laser alignment sensors automatically center the core, ensuring perfect coaxial alignment between the paper tube and the adhesive film. On the opposite side, the coated film roll is placed on a material feed stand equipped with an electromagnetic brake system that maintains consistent tension throughout winding. If tension exceeds 3 to 4 psi, the film can stretch and distort the adhesive surface. If it's too low, the winding becomes loose and prone to peeling. As the machine starts, an air pressure nip roller lightly presses the film against the core, ensuring a uniform bond as the adhesive layer wraps around. Meanwhile, thickness sensors monitor each rotation to maintain consistent layering from start to finish, keeping edge deviation below 1/100th of an inch. Operating speeds can exceed 300 feet per minute, yet thanks to servo-synchronized control between the main and feed shafts, the system runs smoothly and precisely. A micro-air jet unit runs along the winding axis, continuously blowing thin streams of air to remove microscopic dust or trapped air bubbles, a key factor in achieving perfectly clear tape. When the roll reaches its programmed diameter, an automatic separator blade cuts the film between two cores, and a thermal sealing roller smooths and secures the film edge. Each finished roll is gently transferred onto a receiving conveyor, while a new empty core is loaded in seconds, allowing near-continuous operation. Before leaving the station, optical inspection cameras verify each roll's tightness, edge alignment, and surface adhesion. All data is sent directly to the central control system, ensuring every roll of tape leaving the machine meets the highest mechanical and visual standards. After each film roll is completed, it moves into the automated inspection area, where every parameter is measured by sensors with precision down to fractions of an inch. High-resolution industrial cameras scan the entire surface of each roll to detect defects such as edge misalignment, uneven winding, or dust trapped in the adhesive layer. Compression sensors test the roll's tightness, ensuring that tension remains evenly distributed from core to surface. Any deviation beyond the acceptable tolerance is automatically flagged and separated for rewinding or recycling. Compliant rolls continue to the dimension and labeling stage, where their weight and width are verified before automatic printers apply batch codes, production dates, and adhesive type. Some factories also add QR codes for traceability, allowing every roll to be tracked throughout the entire distribution chain. Before packaging, a soft press roller smooths the outer layer and releases residual air. Each roll is then wrapped in PE shrink film to protect it from dust, humidity, and mechanical impact during transport. Robotic pick-and-place arms stack the rolls into cartons or bulk trays, typically 36 to 72 units depending on size, and seal them with the very same adhesive tape, closing the loop of its own production process. Once complete, pallets are wrapped in stretch film, labeled with barcodes, and transferred to the dispatch zone. Here, automated scales confirm shipment weight before robotic lifters load them onto trucks. From the winding line to warehouses around the world, each finished roll of adhesive tape begins its journey, serving industries from manufacturing and packaging to construction and logistics. When the final pallet of adhesive tape leaves the production line, upstream in the supply chain, a new cycle begins, as polypropylene pellets are once again created from petroleum and natural gas, marking the start of the material's next life. The journey begins inside a polymerization reactor, where gaseous propylene combines with a Ziegler-Natta catalyst under pressures of around 450 psi and temperatures exceeding 300 degrees Fahrenheit. Here, propylene molecules link together to form long polymer chains, producing polypropylene, PP, a plastic prized for its tensile strength and moisture resistance. After the reaction, the polymer mixture is cooled and extruded through steel dies to form fine strands, which are then cut into uniform pellets about 1/10 of an inch long. A stream of forced cold air keeps the pellets separated and prevents them from sticking together. Before packaging, the material is dried at 210 to 230 degrees Fahrenheit to remove any residual moisture, since even trace amounts of water can cause defects during the later film extrusion process. Each 55-pound bag of PP pellets is sealed and shipped to adhesive tape factories around the world, where the next chapter begins as these raw plastic grains are transformed into the thin, transparent film that wraps around every industrial product of the modern age. From polypropylene pellets to the rolls of tape that bind the industrial world together, this journey reveals humanity's ingenuity in turning raw materials into essential tools of modern production. Each roll of adhesive tape is more than a product. It's the outcome of hundreds of intricate steps where chemistry, engineering, and precision work in perfect harmony.